Alright, let's dive right in. Today we're going to talk about a force you used your entire life, but maybe you don't really get it magnetism. We're going to pull back the curtain and find the tiny atomic sources of that invisible push and pull. So let's do it. I mean, we all know what magnets do, right? They stick to your fridge, they snap together, they can even float. But have you ever stopped and really wondered why? What is actually going on inside that piece of metal to create that mysterious force? Well, to answer this isn't something you can see on the surface of the magnet. The real secret to understanding every single magnet in the universe, from that little one holding onto your grocery list to the giant magnetic field protecting our planet, it all boils down to one single fundamental building block. And here it is, the magnetic dipole moment. Now, this is it. This is a bedrock. The basic unit of all magnetism. You can almost think of it as the atom of magnetic force. Absolutely everything we are about to talk is built from this one idea. Now, I know magnetic dipole moment sounds a little intimidating, doesn't it? But the concept is actually super simple. Just picture this. Inside every single atom, there's a tiny invisible compass needle. That's it. This little needle has its own north and south pole and it can spin around and point in any direction. That little compass, that's our magnetic moment. Okay, so where do these tiny atomic compasses even come from? What creates some in the first place? Well, to get our heads around that, we are going to start with the classic physics idea that works as a perfect analogy, the current loop. Say it's one of the fundamental rule of the universe. Moving electric charges create magnetic field. So just imagine an electric current, which is really just a bunch of charges flowing together, and imagine it's moving in a circle, a loop. That motion right there generates a tiny magnetic field. And just like that, you've created a magnetic moment. And what do we have moving around inside every single atom? Electrons. This is the absolute key. The entire story of magnetism is really just a story of electron and how it moves. But hold on, because the current loop idea is just an analogy, the true sources is even more fascinating and it takes us deep into the weird worlds of quantum mechanics. Turns out the electron is hiding a secret. It doesn't just have one way of making a magnetic moment, it has two. So here are the two electrons' secret. First, you got the orbital moment. This one's easy. As an electron orbits the nucleus of an atom, it's actually exactly like that little current loop we just talked about, creating a magnetic field. But then there's a spin moment, and this one is wild. It's a purely quantum thing. The electron has its inbuilt intrinsic magnetism just by existing. It doesn't have to be orbiting anything. It's as fundamental to what an electron is at its negative charge. It just has it. Okay, so we've established that atoms have these tiny little magnets inside them. But what happens when they run into a bigger external magnetic field? Like when you bring a piece of iron near a magnet, uh, so the very first thing that happens is that our little magnetic moment feels a twisting force, a torque. It tries to rotate and snap into alignment with that bigger field. Just like a compass needles always want to point towards north. But it gets even cooler than that. What if the big magnetic field is in the same strength everywhere? What if it gets stronger the closer you get to the magnet? Well, in that case, the little moment doesn't just feel a twist, it feels a pull. A real force actually starts dragging it towards the stronger part of the field. So at the end of the day, a tiny magnetic moment really does act just like a miniature version of a power magnet. You can hold it in your hand. It wants to line up with the field. It gets pulled towards stronger fields. And don't forget, it's also making its very own tiny magnetic field. This behavior is key to everything that comes next. Alright, it's time to zoom out. We've been discussing on a, and only focusing, I meant, we only focus on a single atom, which is incredibly small, but real world materials are made up of trillions and trillions of these things. So, what happens when you pack all these tiny atomic magnets together in one place? Well, whether a material is super strong magnet or a weak one or not magnet at all, it completely depends on what all those tiny atomic compass needles are doing collectively. Are they all organized pointing in the same direction like a chain army, or are they all pointing in random directions, canceling each other? To measure this, we use a term called magnetization. All it is a measure of a total combined magnetic moment in certain amount of stuff. So if you have a high magnetization, it means ton of those little atomic compasses are aligned and working as a team. Low magnetization means they're all just chaotic mess. Okay. Next up, we got something called a magnetic susceptibility. This is all about how easily a material lets its little moments get aligned. Think of it as how persuadable the material is. Something with high susceptibility, like iron, is super easy to convince. You bring a magnet nearby and its atomic moments snap to attention. But something with low susceptibility, like say a piece of wood, just doesn't care. And finally, there's permeability. So this one is really important. It measures how well a material can support and even amplify a magnetic field. Materials with higher permeability can actually gather up magnetic field lines and concentrate them, making the field inside way stronger. So that's it. So these are the three properties, um, and that's the secret. Every single magnetic field you have ever experienced in your entire life, it all starts with spin and orbits of single solitary electron. It's just this beautiful, powerful link between the bizarre quantum world and the world we see and touch every day. And of course, that leaves us with one final, pretty obvious question to chew on. If every atom in the universe has these little magnetic moments inside, why isn't everything magnetic? Why can't I stick my coffee mug to the fridge? Well, as we've just seen, the secret isn't just having the tiny compasses, it's about getting them all to point in the same direction.